have a Baconator meal.
The Baconator double?
Yep. Find out how much energy is in a Baconator. All right, thank you. That's for Baconator.
This is Thermite. It's a powdered mixture of iron oxide and aluminium, which when ignited burns at 2,500 degrees Celsius, which is very, very hot. This is liquid nitrogen. It's specially stored at minus 198 degrees Celsius. That's 163 degrees colder than the North Pole in winter. But is it cold enough to neutralize the intense heat of thermite? Packed into the slow-release mechanism of a garden flower pot, the thermite is ready for action. Just light the touch paper and stand well back. The fuse triggers the irreversible thermite reaction. As scorching hot meets freezing cold, a fierce battle rages. The smoke clears, and incredibly, nothing remains. As the thermite burns at 2,500 degrees, it releases a raging torrent of molten iron, which rains down upon the liquid nitrogen, boiling the glacial mixture away in a plume of vapor and melting the cylinder, leaving just a puddle of white-hot iron. A clear victory for thermite. So there you go, Dan. Adding something cold to thermite doesn't cancel it out. It just makes it angry. Thermite. You won't like it when it's angry. This is a car. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of a car. It's basically a huge lump of metal, and well, it's very hard to melt. Lucky then, the Brainiacs have plenty of thermite, specially packed into the slow-release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Within seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine. Now that the engine is melted clean through, it seems only fitting to have a go at the petrol tank. Packed into the slow-release mechanism of a garden flower pot, the thermite is ready for action. Popped onto the roof, directly above the fuel tank, top up, and just 4 feet of family car stands between the thermite and 8 gallons of petrol. Light the touch paper and stand well back. The irreversible thermite reaction begins. Thermite produces a stream of molten iron which melts through the car in seconds. It's 2,500 degree heat igniting the expanding petrol in a devastating fireball, leaving behind a car that won't be going very far anytime soon. So there you go.
So how many thermite reactions are in a Baconator? So what we're going to do is we're going to figure that out. First, we need to figure out a little bit more about the thermite reaction. So it says write a balance equation for the thermite reaction. And it says to refer to C for the reactants. So given that 50 grams of iron 3 oxide and 18 grams of aluminum powder react, All right, let's make that equation. So if I have iron 3 oxide and it reacts with aluminum powder, all right, let's get some states of matter in here. What's my reaction? Well, that looks like a single replacement reaction. So the Al is going to kick out that iron, which is making molten iron in thermite, and the aluminum is now going to be bonded with that oxygen. Every time you make a compound by itself, it should be a singular element, except if it's a diatomic. Every time you put something together, check your charges. Aluminum has a 2 minus, and oxygen has 2 minus, aluminum is a 3 plus. And these are actually both going to be solids as well. Okay, let's balance that. 2 here and a 2 there. Right. B. Calculate the change in enthalpy for the reaction. Use the enthalpy of formation values. All right. Well, first, I already know that these are going to be 0, but we're going to look them up anyway. The elements are going to have 0. And the reason why is it doesn't take any energy to create the elements when they're already elements. But let's look at our selected thermodynamic values. So first, I'll prove it to you. We're looking only at the enthalpy of formation. Aluminum is 0, but aluminum oxide is basically negative 16, let's say 76. So we're going to put that underneath. Okay. And my iron is just organized by elements. Looks like it's about negative 824. Right, Fe2O3, 824. All right, so when we say calculate the change in enthalpy, that's products minus reactants. So when I'm doing this, a reminder, this just is for the total reaction. This means at standard conditions. So that I have my products, I'm subtracting my reactants. In this case, I have my product, which is aluminum oxide, I'm subtracting my reactants, which ends up being my iron 3 oxide. Right? So what do you get? Roughly 852 kilojoules per mole, technically. Okay, so that is how much enthalpy is flowing through this reaction. It is definitely an exothermic reaction. Letter C. Given that I have 50 grams of iron 3 oxide and 18 grams of aluminum powder, how much energy is released? Okay, so this is per mole, but now I'm given a specific amount, okay? So this looks like it is a limiting reactant problem. So what it is saying is that I have 50 grams of the iron 3 oxide and I have 18 grams of my aluminum powder. So let's see how I would do that. If I have 50 grams of the iron 3 oxide, okay, and I have 18 grams of aluminum. If you would do a little T-chart, okay, I'm going to tell you right now that this is that many moles, and the aluminum has this many moles present. Well, how do you figure that out? How do you determine the other one then? Well, it is all about a ratio. So notice that is a 2-to-1 ratio. So if I would take this iron 3 oxide, and I would basically say, okay, for every 2 moles of aluminum, I have 1 mole of iron 3 oxide. And I would take this and do the opposite, because I'm trying to figure out which one is the limiting reactant, right? And I'd say I'd have 1 mole of iron 3 oxide. It's 2 moles of aluminum. Which one's the limiting reactant? Without even having to calculate it. I mean, look at this right here. Just calculate this. I would have 0.626 moles of aluminum needed. Okay, you didn't have to do both. Look at, I need that much, and I have that much. I have more aluminum than I need. So automatically, I'm done figuring that out. My Fe2O3 is my limiting reactant. So I'm going to utilize that many moles, and let me show you what that means. Is that if this is the amount of energy that's released per mole, all right, well, I have 0.313 moles of iron 3 oxide, right, in per one reaction. So now I can say, well, I have 152 kilojoules per every 1 mole. So I have roughly 266.7 kilojoules in one reaction. All right. So, I had to cut that off accidentally. Final question. Assuming there are 950 food calories in a Baconator, how many thermite reactions are equivalent to the energy content of the Baconator? So what I'm basically going to ask you now is, if I eat a Baconator and I put that much energy into my body, how many thermite reactions did I just swallow? Okay? So I would love for you to pause this and try to figure it out yourself. So I'm going to give you the starting point on this. So I'm going to say 1 burger or 1 Baconator. All right? And what we're going to try to figure out is the number of thermite reactions. So my final answer should have the word reaction. Okay, that's my unit. I'm going to give you a big hint. So I'm going to start with this. I have 950 food calories in 1 burger. Okay, so I'd love for you to pause this and see if you can figure out how many reactions, and you can round up or down how many reactions are in a Baconator. So please pause it. All right, let's see what you got. So use my conversions, and units are my guide. So I have 1 food calorie equals 1 kilocal. 1 kilocal equals 1,000 calories. For 1 calorie, there are 4.18 joules of energy. If I want to get energy into the more appropriate unit, I would say for every 1,000 joules, I have a kilojoule. And then for every 1 reaction, there's my unit, I have 266.7 kilojoules of energy. So I get 14.88 reactions. So 15 thermite reactions, approximately, are in 1 burger. 15 thermite reactions are in 1 burger. That's incredible. Think about that. All right, so for summary, what we did was we utilized our enthalpy of formations from a given reference sheet. All right, you take those formations, you take products minus reactants, and that will give you the overall enthalpy for that reaction, and then you can do a lot with that, from converting in T-charts to understanding the overall energy flow. So that